Welcome to the presentation. The title of the paper is Formal Synthesis of Trajectories for Unmanned Aerial Vehicles to Perform Resilient Surveillance of Critical Power Transmission Lines. It is a collaborative work between three different institutions. I am Muhammad Ashikur Rahman from Florida International University, Rahat Masoom from Tennessee Technological University, Matthew Anderson and Stephen Drager from Air Force Research Laboratory. This talk is outlined in the following order. First, we'll talk about motivation, then literature review. Then we'll discuss the research challenges and contributions. We'll briefly go through the solution framework and technical approach. Then we'll show some evaluation results. Then we'll conclude this talk. Power grid transmission and distribution systems use overhead power lines to transmit electrical energy along long distances. Any physical damage to these power lines will lead to outage or unstable situation. The reason is mostly the natural calamities, equipment aging, technical errors, physical attacks or terrorist attacks. So power line surveillance is very important to assess and fix anything incurred or the potential physical damages. To understand the potential damages, special properties like the infrastructure health, temperature, elongations, they are crucial to be investigated. Transmission line surveillance traditionally use event-based actions. However, this is reactive process, so it delays the recovery steps. Hence, continuous monitoring of these transmission lines is beneficial, especially to allow quick and proactive fixes. Surveillance is not like an easy task, as we can see that it goes through deep forest, long rivers, remote coastal and hilly areas, and even it can go through busy cities. Now, how this transmission line surveillance is being performed. One traditional approach is human patrol based. However, this approach is highly inefficient with respect to time and safety. There is another approach that sends trained inspectors. They fly with helicopters. However, it is unsafe again, especially in extreme weather conditions, and is still time inefficient for remote areas. And obviously, it is expensive, and this approach is fully impossible, especially for continuous surveillance. So, unmanned aerial vehicle based surveillance is a perfect solution. Now we'll define the continuous surveillance problem. To ensure continuous surveillance for the whole power grid is a massive job due to its huge size and geographical distribution. Hence, the criticality of the transmission lines can be considered to prioritize the surveillance. This criticality tells if a line trips or fails, how it impacts the system. The criticality depends on the topology and the generation load structure of the buses. So these surveillance requirements, there are like two primary requirements. The first one is to maximize the criticality coverage. Secondly, the continuous surveillance property that we name as data freshness. And lastly, the K-resilient surveillance property that we define as if K number of UAVs fail or are compromised, still there is a UAV to do the surveillance job. And this surveillance design must consider fuel consumption and refueling plan. So what is our research objective and what are the research challenges associated with them? The objective is like given a set of specifications, that is grid information like bus topology, geographical power line topology, and UV informations, along with the requirements like continuous surveillance, K resiliency. We need to find the K resilient surveillance plan that will include the trajectory and refueling plan for each UV. The challenges basically it is a like a multi-objective problem. We have multiple UVs, many potential monitoring points, and a single mission. We have like a continuous monitoring requirements that is critical coverage and data freshness specifications. We need to be resilient against the failed or compromised UVs, and the plan should be cost effective, and refueling plan needs to be there. So it is a complex problem that is NP hard. In this work, we propose a formal framework for automated synthesis of a continuous and resilient surveillance plan by modeling the problem as the satisfaction of different constraints. Those are related to UV trajectory, continuous surveillance, criticality of the transmissions line, and K resiliency surveillance. We implement this proposed formal model using satisfiability modulo theory or SMT. SMT is a state-of-the-art solver that can solve complex decision problems with millions of clauses. We also evaluate our implemented tool on different synthetic cases that we adapt from various IEEE test bus system. This is the architecture of our proposed formal synthesis framework. For formal modeling, it takes the inputs for UV properties, overhead power line topology, and corresponding power line criticality curve. It takes the surveillance requirements in terms of continuous monitoring, criticality coverage, and K resiliency properties. This model is solved using Z3 popular SMT solver managed by Microsoft Research. And if we get a set answer, that means the our model provides a satisfiable solution. We have the trajectory and refueling plan. So if you want to do further analysis, like we want to get a better trajectory plan based on modified resource limit or requirements, we can go back to the formal model with the changed requirements. In cases where there is no solution, we will receive unset from the solver. In case of unset, we may also like to modify or relax our constraints or increase the resource to get a satisfiable answer. Now we'll briefly go through our formal model. Here we will only provide the logic or intuitions behind the formalizations. To model the trajectory, we assume several properties. First, each line is divided into multiple segments, where each segment connects 2 points on the transmission line, and these segments have the same size. We also assume that the UVs maintain the same speed. Since different UVs may have different characteristics, we assume that they will consider different fuel consumption to maintain the same speed. Now, to model that if a UV visits a point that is P at a particular time instance S, um, it can happen in two cases. In the first case, the UV was at the same point at the previous time instant, that is S-1, and it was hovering. In the second case, it was at a neighboring point P prime at timestamp S-1 and it flies to the current point and reaches here at timestamp S. So to model this scenario, we have this simple formalizations. where we define hover and fly separately. Now, just for an example, how we define or formalize fly, we can see it here. So, UV can fly to point P from P prime when they create a segment. So they are neighboring points, and here we ensure that the UV was at that point at time stamp s minus 1. So we also need to do calculate the fuel consumption. So we do it here. Um, there are like a different parameters we consider. The details you can find in the paper. Here we model the continuous surveillance. First, we consider a point is visited at a particular time instance S. If any UV visits it, we model this part here. Now, for continuous surveillance, each visit must be followed by another visit within a given threshold time. This is the data freshness requirement, but we may exclude the part that is if the remaining analysis time is smaller than this threshold, we may not need to consider that part. So now the point is about this like how we say about like a repetition. So to understand this repetition of this surveillance plan, considering the analysis time, we need to consider a few other more constraints. So if you see here, this is like a time frame where it starts from 1 and then at S. If we want to repeat the whole things, so the constraints we must ensure that the initial and end positions, that is at time instances 1 and S of each UAV will be the same, and the remaining fuel is no less than the initial condition. So these two conditions will satisfy that the trajectory plan that we achieved for this time frame can be repeated continuously. A UV will consume fuel when it flies from a point to another point. This consumption may be different due to the heights or altitudes. So we reflect this scenario using a fuel cost ratio that we take over the cost of flying the same distance horizontally. The UV will also incur cost when it also hover. However, this cost will be less compared to flying from a point to another point. Now to abstract the refueling model, we consider three steps. In the first step, the UV goes from a point to the base stations, and in the second step, it is doing this refueling. In the third step, it returns back to the systems to a particular point and start doing the surveillance. Here we give the formalizations for the first step where we ensure that the UV is refueling when it reaches the station after these time steps that is required to reach the station. And we also ensure in the latter part of this formalization that during this time that UV does not visit any other points in the system. Now to model resilient surveillance, we have two constraints to satisfy. The first one is if it is visited by at least k plus 1 UVs within a given threshold time. This time TR is the data freshness requirement for resilient surveillance. And the second constraint, this is for the continuous surveillance. It ensures that each resilient visit is followed by another resilient visit. Now to measure that, if k plus 1 UVs visited a particular point during the data freshness threshold time, we need to know whether a point is visited by a particular UV during a time period. So we model this part here in these equations, this second equation. Transmission lines criticality is computed using line outage distribution factor, or LODF. It actually reflects the notion of if a line fails, how it impacts the other lines in the system. So performance index is calculated according to these LODF values. So each line will receive a criticality score according to these performance index values, and we use k-means clustering method to find out different criticality levels, and each line that will fail under a cluster will receive the same score. So each point on a line will take the same quantitative score. As we see that there are like two surveillance constraints according to this criticality. So it says like the summation of the criticality score that is point under continuous surveillance needs to be greater than equals to a percentage of the overall criticality. This requirement is taken for both continuous surveillance and the resilient continuous surveillance. We will here demonstrate a simple case study based on IEEE 14 bus test system. The left-hand side, we show the schematic bus topology. On the right-hand side, we are showing a synthetic geographical topology of this system. So in this system, we consider 65 equal length segments that comprise 59 points. As you can explicitly, the line between bus 12 and 13, it has 4 segments. It includes 5 points. This is the partial input corresponding to this case study. We start with the number of buses, lines, points, number of UVs, all this information. Then we take the transmission line information as well as generation and grid information that we didn't show here. We take the inputs regarding the segments and the points and the UV properties. Now about the threshold or the constraints, we have like three main inputs. The first one is the threshold time between two consecutive visits to a point, that is for continuous surveillance. We have the K resiliency requirement. Here it is 2. We have the threshold time for that, it is 45. And the minimum criticality scores that we consider here, that is 80% in case of continuous surveillance, and 50% of criticality coverage for the resiliency surveillance. We received a set answer in this case study, and according to our input, we have seen that there's like a 3 different criticality levels. And in case of trajectory plan, we see that for the continuous surveillance, 45 points are under this requirement that covers around 81% of the criticality. And in case of like resilient surveillance, we have 28 points under this coverage, and that cover a little over the 50% of total criticality. As we can see that in case of like this resilient surveillance, it covers 62%, 48%, and 40% of the high, medium, and low critical points, as we have like a 3 critical levels. So now, why is that? So it happens that why not all the highest critical points were visited? Due to the distribution of the higher critical lines in the topology in different geographical locations and the limited number of UVs, we cannot cover all the critical points. Rather, we need to cover like a less critical points, some cases, to keep the continuous surveillance happening. Here is an example of like a trajectory for point 10 when it is visited. So if we can see that it is visited at time 23 by UV1, time 43 by UV4, and so on. So here, this particular point 10, it is continuously surveilled and it is also resilient surveillance ensured. We analyze the characteristics of surveillance planning by evaluating the minimum number of UVs to perform this job. The evaluation is performed based on different synthetic grid infrastructures that are driven from IEEE test bus systems. In our evaluation, we consider different surveillance requirements and different system sizes. We vary these values to see their behavior. We perform the scalability analysis in terms of the execution time. Our experiments we ran on an Intel Core i7 machines with 16 GB memory. Now we'll present some of the evaluation results. Here in the left graph, we show the impact of the criticality coverage requirement on the number of UAVs to do the surveillance. As we can see, the more is the criticality coverage requirement, the higher is the number of UAVs to do the surveillance, but this increase is sublinear. In case of like impact of the criticality distribution over lines on the number of UVs, that is our second figure, it shows that the more is the criticality covered by a small part of the transmission lines, the easy it for the UVs to cover the criticality. In this particular case, we consider 70% as the criticality coverage requirement. But since when, for example, in case of like a 50% criticality, when it is covered by 30% of the top lines, we see that the number of UVs required to do the surveillance is much less compared to the case when it covers like 35% of the total criticality. Here we present some scalability analysis results. On the left-hand side, we shows the impact of the resiliency requirement on the execution time. As we can see, if we increase the resiliency requirement, the execution time grows rapidly because with a fixed number of EOVs, it becomes harder to find the surveillance plan. On the right-hand side, we present the impact of the number of EOVs on the execution time. As we can see in the beginning, when the EOVs are increasing, it becomes easier to find the surveillance plan. But after a point, due to the increase of the number of clauses of the formal model, it keep increasing the execution time. So we can see there is an optimal situation of this execution time. So in summary, we have proposed a formal framework that can synthesize a continuous and resilient surveillance plan according to the given constraints or requirements. We have implemented the proposed solutions. We demonstrated it on case studies, and we also evaluate its characteristic analysis and doing the scalability analysis as well. So in the future, we would like to use like appropriate 3D aspects of the UAV moves, and we also like to investigate the reinforcement learning to find resilient trajectories. Thank you for listening to my presentation. If you have any questions, please email me. I would love to answer them. Thank you. Bye-bye.